Hi, welcome to another lecture on ME 201 fluid mechanics. In the last lecture, we have discussed about the very interesting and useful concept called continuum hypothesis. Okay, so in this lecture, we'll be discussing a few properties of fluids. Okay, so let us start with some properties that measure density of a fluid. So you know that density is defined as mass over unit volume, right? We know this already. Okay, so there is another quantity to measure the density is specific weight, which is denoted as gamma, which we define as weight of the fluid per unit volume. Okay, and the another one is called specific volume, which is the reciprocal of density, which is volume per unit mass. Okay, and there is another quantity called specific gravity, okay, which is used to denote density of any liquid, and it is defined as density of the liquid by density of water at 4 degrees centigrade. Okay, we know density of water at 4 degrees centigrade, which is 1000 kg per meter cube. Okay, so the unit of density is kg per meter cube. Our specific weight is Newton per meter cube, and specific volume being the reciprocal of density, this will be meter cube per kg, and specific gravity is the ratio of two densities, so this will have no units. Okay, so specific gravity is used to denote density of liquids, used in liquids. Okay, so all these four measures mass or weight of the liquid under given volume. Okay, and these are all very simple one which already know. Okay, and second important one we'll move on to discuss is the viscosity. Okay, so how many of you remember Newton's law of fluid now? What is a Newtonian fluid? Okay, so there are fluids for which the shear stress is directly proportional to the rate of strain. Okay, and the coefficient of proportionality is the dynamic viscosity. Mu is what we call as dynamic viscosity. Okay, so fluids that obey this law are called Newtonian fluids, and this is called Newton's law of viscosity. Okay, so what does this mu or dynamic viscosity physically implies? Okay, in order to see that, again let us consider this simple example. Okay, where we have fluid between two plates. The bottom plate is stationary, and at the top we apply a constant shear stress. Okay, and we will consider a few fluid particles that are lying like this. Okay, so this particle is located very close to the top surface, so this will move at a very large velocity, right? and this one which is very close to the bottom plate will move at a smaller velocity, and this will have an intermediate velocity between the top and the bottom layer. Okay, so what happens is that this layer that is moving at a smaller velocity, due to the cohesion between molecules, the intermolecular forces and the random collision, what happens is that this tries to slow down let us number this as 1 2 1 3. So this tries to slow down the particle number 2. Okay, so that is due to the intermolecular attractive forces between these two particles. Okay, and it also is due to the collision. Okay, so there is a friction or the internal fluid force that offers resistance to the relative motion of layers of fluid, right? And viscosity is a measure of this internal resistance force. Okay, so viscosity is the measure of internal fluid friction that offers resistance to relative motion between layers of fluids. Okay, do you understand from this picture? We have considered, let's say, 3 layers, 1 2 and 3. So the bottom one moves with a smaller velocity, and the layer slightly above moves with a larger one. Due to the cohesion or the intermolecular forces and random collision between the molecules, the layer 1 will try to pull down layer 2, and in turn layer 2 offers resistance to the motion of layer 3 due to the same mechanism of cohesion. Okay, so dynamic viscosity is a measure of this resistive force that is offered between relative motion between layers of fluids. Okay, is that clear? Yeah, so the physical origin of viscosity is the cohesion between molecules and the molecular momentum transfer due to random collisions. Okay, in liquids the collision between molecules dominate, and in gases the random molecular motion and the associated momentum transfer dominates. Okay, so there is an internal mechanism in a fluid that offer resistance to relative motion between layers of fluid, and dynamic viscosity quantifies this internal fluid friction. Okay, and so what happens when we plot the temperature and viscosity of the fluid? Okay, so I'm going to draw 2 curves. Okay, for one in which the viscosity decreases with increasing temperature, for the other the viscosity increases. Okay, can you guess which one is a liquid and which one is a gas, and why? Can you pause a moment and guess which one is a liquid? Okay, so the red one is liquid. Okay, because in liquids the viscosity is dictated by the cohesive force between molecules. When you heat the liquid, this cohesive force weakens, and as a result the viscosity reduces with increasing temperature for a liquid, whereas for a gas, okay, the cohesion is already small. The viscosity is dictated by the random collisions and the associated molecular momentum transfer. And when you heat up the gas, the random motion of the molecules gets enhanced, and as a result viscosity increases for a gas. Okay, so there is another definition, there is another viscosity which is defined, which is called kinematic viscosity, which is denoted as nu, which is the ratio of dynamic viscosity divided by the density of the fluid. Okay, so is it clear what do we mean by physically viscosity, and what really causes, or what is the physical origin of viscosity? I hope this is clear. So we will discuss one more property called compressibility, and we will stop this lecture. Okay, the other property is compressibility. Okay, so compressibility measures how easy or difficult is it to compress a fluid, okay, which is given by a bulk modulus. Okay, do you remember what a bulk modulus is? By K, which is P by B. So a bulk modulus is defined as the amount of pressure required to produce a unit change in a specific volume. Okay, so here V is specific volume. Okay, so we have a negative quantity here because when pressure increases, the quantity dV by V decreases, but it is a modulus, so we want to have it as a positive quantity. That is why we have introduced a negative here. Okay, so you know that density is 1 by V, but density is reciprocal of specific volume, so this can be written as dP is d rho by rho. Okay, so bulk modulus is inverse of quantity called beta, which is coefficient of compressibility. Okay, so to understand the bulk modulus, let us consider a simple piston cylinder arrangement. Okay, this is a piston cylinder arrangement. You fill the fluid here, and this is subjected to pressure force P. The amount of pressure force you need to supply to the piston to produce a unit change in density is what is quantified by the bulk modulus. Okay, is it clear? So now the d rho by rho can be written as dP by K. Okay, so this d rho by rho is the amount of a unit change in density. The bulk modulus for is the bulk modulus. So bulk modulus for water is 2.2 10 to the power minus 9 meter square. The same quantity for air is 10 to the power 5 Newton per meter square. So approximately 4 orders of magnitude difference in bulk modulus. This is the reason why air can be compressed very easily when compared to water, because the amount of pressure required to produce a unit change in volume is smaller for air. Okay, is that clear? So a fluid can be considered incompressible. Fluid can be considered incompressible if K, the bulk modulus, is very large, okay, or the velocity of the flow is not very large. Okay, so what you see here, if K is very large, the density difference produced is very small, or if dP, the pressure difference produced, is very small, then also the density change is not very significant. Okay, so when the fluid flow is happen at a very small or not very large velocity, the pressure difference produced is not significant. Okay, so even in that case, we can consider the flow of a particular fluid is as to be incompressible. So air, although has very small bulk modulus, or not very small, but much smaller bulk modulus, at small velocities, okay, can be considered as incompressible. Okay, so it is given by this non-dimensional parameter called Mach number, okay, m, which is velocity of the fluid divided by speed of sound, okay, E by A. If the Mach number is less than 0.3, then we say that the flow is incompressible. Okay, so incompressibility, so because of this second point, okay, incompressibility is not really property of a property of a fluid. It is actually the property of the flow. Okay, an incompressible flow is one in which, so when we say incompressible flow, we mean that density is not a function of pressure. Okay, so density is independent of pressure. So density can change with respect to temperature, but density is not a function of pressure. Then we say the flow is incompressible. Okay, so when we say incompressible flow, we are not saying density is constant. Okay, that is not correct. Density need not be constant. It's only when we say incompressible flow, we are talking about density is not a function of pressure. Okay, so we'll close this lecture with this. Thank you.